So, good evening, everyone. Welcome to the 12th and the final live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Arshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay. So in today's session, we will first have a recap of week 11 session that we concluded last week, and then we'll have a review of week 12 run learnings. So in week 12 recordings, they were oriented towards design of two-way reinforced concrete slab. So in this today, we'll first start with discussing a basic overview of slab design, understanding the difference between one-way and two-way slabs. Then we will particularly look deeper into the background and the design of two-way slabs. In the design part, we'll see IS provision of design, direct design method, and equivalent frame method for two-way slab design. So today, along with the quick theory recap for different segments, I will introduce you with several questions, both numerical and theoretical. So in total, there will be around 15 questions that we will discuss today. And in the end, I will make myself available to solve any other queries post discussion. So last week we started our discussion on serviceability criteria of reinforced concrete design. So we know limit state design method is commonly practiced for reinforced concrete design, which has two parts: limit state of design and limit state of serviceability. Now in this, if we just focus on design, we design for worst possible loading conditions. But in reality, in actual loading conditions, we also don't want excessive serviceability issues in reinforced concrete. So here is when this serviceability limit states comes into picture, which provides a limit on reinforced concrete condition in service loading condition. So serviceability we can judge based on two criteria: deflection and cracking. And why deflection is important, why deflection check is important? Because of four main reasons. First is visual appearance, second is damage to non-structural elements, disruption in functioning, and damage to structural elements. In deflection, we saw two types of deflection: short term deflection and long term deflection. So, in short term deflection, we talked about cracked concrete section. For this, if moment is greater than the cracking moment, we need to find deflection based on effective modulus of elasticity, moment of inertia of concrete. So for this I effective, we derived this formulation of how I effective is dependent upon uh, moment that is acting on the section, cracking moment and cracking I value, and neta. And this neta factor, we related it with the neutral axis depth and other dimensional parameters of a reinforced concrete. In long term, we first discussed about the effect of shrinkage. We discussed about this relation of curvature in a reinforced concrete beam due to shrinkage, and how it will depend upon the relative proportion of reinforcement that is present in the tension side and the compression side. So based on this relative proportion, how we get the curvature in a reinforced concrete beam due to shrinkage. Then, after deflection due to shrinkage, we discussed about deflection due to creep. We saw this formulation of change in moment of modulus of elasticity of concrete due to creep based on the concrete loading gauge and respective creep coefficient, which is represented by theta. And then again, considering different load combination, cracked section, and creep effect of creep, how deflection due to creep is estimated, that we saw. Then we saw how IS 456 code imposed limits on total deflection that were less than L by 250 and less than L by 350, depending on the type of combination of deflections that we are considering. And in case these limits are exceeded, how code says to tackle the problem of deflection, either by providing camber, or by increasing the section depth, or by changing the grade of concrete, changing the effective span of concrete, or by providing compression reinforcement. So there are different ways in which deflection can be tackled. Now, every time calculating deflection can be a tedious process. So, just based on L by D ratio, we can have a judgment whether the total deflection can be under control or not. This L by D ratio, as per IS 456, is based on basic value that we can get from part A of clause 23.2.1, and some modification factor which are imposed on this basic value based on the span length if it is greater than 10, percentage tension reinforcement, percentage compression reinforcement, and flange to web width. After deflection, we talked about cracking in reinforced concrete. We saw different types of crack and why cracking occurs and why cracking is a problem for reinforced concrete. We discussed how we can estimate crack width at a particular location on concrete cover. And as per IS 456, we derived this formula, and where ACR is the distance of crack from the nearest longitudinal bar, sigma m is the average steel strain at the considered level, and this constant, it depends upon the type of bar, whether it is a deformed bar or a plain bar. And finally, we discussed about bond between embedded steel reinforcement and concrete. Here, for ensuring that slip of rebar doesn't occur and full bond strength is developed, we need to provide a certain development length. And for determining the development length, we saw this formula based on IS 456, which says that LD is equal to sigma phi times Fs upon 4 tau BD. Phi is the diameter, Fs is the stress in steel, and tau BD is the bond strength between steel and concrete, which we can get from this table, which is given in IS code. Okay, so this was all from last week's discussion. So for the final section of the course, we will discuss about design of reinforced concrete slab. So if we see a very basic description of slab, we can say that slab is a crucial structural element and they are used to provide flat surfaces in terms of floors and ceilings in a reinforced concrete building. And from technical point of view, we can say slab has two key descriptions. First, their thickness is comparatively less than the length and the breadth of the section. And second, they are used to transverse load acting on the floor to beam or column support by bending in one or more direction. So these two are like basic points which can help us to define how a reinforced concrete section can be set as a slab. So these are key points related to slab. Now, there are three types of slabs based on location. Okay, there is individual slab, so like single slab which is supported on a simply supported system. Okay, so such slab they bend like this. Then there is continuous slab which have multiple supports. So there is support here, here, here. Okay, so such slab they have both negative moment and positive moment, and they bend like this. In term, if I draw bending moment, it will look like this. And then there is cantilever slab. Okay, so these are like this long slab which is supported on one side, and they will bend like this. Okay, so there can be different types of slabs based on the location. Now, before moving ahead, we will just recall what IS 456 code says about slab design. So here in the table, it shows several key parameters that are related to the design of slab and their requirement criteria. So there is effective span of slab, okay, which we can get from clause 22.2. For a simply supported slab, this clause says that the effective L effective of slab, it is given by clear span plus effective depth or center to center distance between the support. So suppose this is my slab and these are my support. Okay, so clear length is this between support L naught. Okay, I know the depth, effective depth of my slab, and I know the center to center distance between the support. Okay, so either it will be L naught plus D, or it will be L naught plus S. Okay, if this is S, if I assume this dimension is so S by 2 plus S by 2, it will be S. So minimum of these two values will be my effective span of my slab for a simply supported slab. Other cases also it is mentioned in the code, like for different cases how this effective length value will change. Then L by D ratio that we can get from clause 23.2. So this is again from the deflection limit check that we saw in the serviceability criteria. Based on that, we get the initial D values. Okay, suppose we know the length of the slab, then how to, while designing the slab, we initially assume a D value, and that value we get from clause 23.2. Then minimum reinforcement. So code says that minimum 0.12% of gross sectional area shall be provided as longitudinal reinforcement, and this is as per clause 26.5.2.1. Maximum diameter of bars, so not more than 1/8 of the slab thickness Okay, so whatever diameter we are using for reinforcement should not be more than the 1/8 of the slab thickness. Spacing between the main reinforcement shall not be more than the 3 times the effective depth in 300. Distribution reinforcement, which are provided in transverse direction, it should be either 1.12% of gross sectional area if we are using high yield steel bars, or it can be 0.15% of area if we are using mild steel bars. And concrete cover, it should not be less than 25 or 2 times the diameter of bar. So these are some basic design parameters and their requirement criteria which is mentioned in IS 456. Now, based on the dimension and the structural property, a reinforced concrete slab can be categorized into four types. There is one-way slab, two-way slab, and flat plate. Okay, so these flat slab and flat plates, they are the part of two-way slab only, but I have listed them separately because of their structure. Okay, so if we first talk about one-way slab, IS 456 code says that when the ratio of longitude longer to the shorter side is greater than or equal to 2, then we say it is a one-way slab. So this is my longer side that you can see here, and this is my shorter side. Okay, so this ratio of Lx by Ly, if it is greater than or equal to 2, then we say it is a one-way slab. Okay, now what are the key features of one-way slab? So these slabs are supported along two opposite directions such that the load is carried along one direction only. So you can see here from the diagram also, these slabs are supported only along two directions. Okay, so load distribution occurs along these two directions only, and they are made to span along the shorter direction, so they will bend like this along the shorter direction. Okay, now in terms of reinforcement detailing, in these slabs we provide main reinforcement along the span direction. So along this direction we will provide the main reinforcement, and we provide some distribution reinforcement along the longer direction in the transverse direction. Why? To distribute any kind of unevenness that can occur due to loading, and for temperature and shrinkage effect also we need to provide some distribution steel reinforcement, and for that only we saw this limit that is mentioned in IS code. Okay, so in one way slab, once we design for longitudinal reinforcement, this is how we provide the distribution reinforcement in the transverse direction. Now, where we will find such one-way slab in practice? So they are commonly designed for verandas and chajjas where load requirements are relatively less. Okay, so in such places you will see one-way slab are present. Now for two-way slab, IS code says that when the ratio of longer to shorter length is less than 2, then we say it is a two-way slab. Okay. So what are the key features of a two-way slab? So we can see these slabs, they are continuously supported on all four sides, and load are carried to supports along both the directions. So you can see in this diagram. Okay, now there are supports that are present on all four sides. Okay, so load distribution occurs on all four direction, and they are made to span along both longer and shorter direction. Okay, so in both the direction these slabs they can bend. Okay. In terms of reinforcement detailing, so we can see main reinforcement are provided along both the direction to resist two-way bending. Since this slab is bending around both the direction, we need to provide reinforcement along both the direction. So you can see in this diagram also. Okay. So along this L1 direction also there is bending, and along this L2 direction also there is bending. So we provide main reinforcement. We design for reinforcement along both the directions. Okay, and now where will find such two-way slabs in practice? So these slabs are commonly designed for multi-story buildings, but multi-story buildings and floor where load resistance demand is very high. Okay, so when load resistance demand is high, we go for two-way slab, and when load resistance demand is generally low, we go for one-way slab. Now, apart from these two major classifications, there can be other sub classifications also, which includes two beams connected two-way slab, flat plate, and waffle slab. Okay, so first in beam connected two-way slab in this system, the support beams provide the moment interaction with columns, especially when the moment resisting frames are used to resist the lateral load. So you can see there is slab, there is beam, and then there is column. So load is transferred from slabs to beams along both the direction, and then from beam the load transfers to columns. Okay, so these are beam supported two-way slab. Then there is flat plate. So in this it is a two-way slab, there is no supporting beam and just directly column. So here you can see slab is directly connected to column and there is no beam in between. Okay, and these slabs are they are used for light load application, not for heavy load applications. Then there is flat slabs. So you can see in this there is slab, two-way slab, which is supported by column with the help of a column capital and drop panel. So this rectangular small panel that you can see, it is known as drop panel, and this trapezoidal panel that you can see below drop panel, it is known as column capital. Okay, so using these two elements, the slab is connected to column, and this system is appropriate for heavier load. Okay, so here what can happen, there can be chances of punching shear failure which can occur. However, when we provide some drop panels and column capital, we can reduce the chances of shear failure, and that's why it can encounter heavy loads also now. And finally, we have waffle slab, okay, which is constructed by orthogonal sets of rib with solid part of column. So you can see these are columns. There is a solid part here, and there is a waffle kind of pattern everywhere around. So what these waffle kind of pattern do, they reduce the weight of the slab, and for these ribs to create, we need specialized foam works in the form of glass fiber and metal domes. So though it is fancy looking and it is lightweight, its construction is expensive compared to other types of slabs. Okay, now based on this basic understanding about slabs, based on different dimensions, just try to answer these simple questions. And in the meantime, if you have any doubt related to the discussion that we have till date, till now, you can ask. Okay, so what will be the answer for first question? Can anyone tell me? Which of the following statements regarding reinforcement detailing in slab is incorrect? So what will be the answer for question number one? Any idea?
Think D should D.
What? I
D,
am not able to hear you clearly.
D, D.
Okay.
Uh,
Any other thing? This is one way slab. Okay. Correct answer will be B for this. Okay, so what B option says, in two-way slabs, equal reinforcement is provided in both the direction, which is not true. Okay, it is not necessary that equal reinforcement needs to be provided. It depends upon the stiffness and the support condition. Okay, so if you look in the course, you saw how this load distribution occurs in two-way slab. So you can see in this third diagram, this B diagram. Okay, so distribution, it is not so there is a difference between one-way slab and two-way slab in terms of design. In figure A, you can see that in one-way slab, uh, along only one direction it is supported. So moment is maximum along one direction and very low along the second direction. But in two-way slab, there is moment along both the direction, and these two moments are not equal. Because load distribution along the two direction, it won't be the same. It will depend upon the stiffness of these ends and the load which is distributed. So generally along the longer side, you will see more load is distributed compared to the shorter side. So reinforcement detailing along longer side and shorter side, it will also be different. Okay, second question, can anyone tell me the answer? A flat plate system is most likely to fail due to, so in a flat plate system, which failure is critical?
Punching shear.
Yes, so we saw just in the last slide that In flat slab, since slab is directly supported by the column, there can be chances of punching shear failure which can occur at the joint, and that's why they are suited just for light load applications. Okay. Third question: what is the main advantage of a waffle slab system over a flat slab system?
C.
Yes, the correct answer is C. Why? Because we are reducing the weight. Okay, when we create such waffle slab system, we are reducing the weight of the slab. Okay, so in turn we increase the stiffness to weight ratio of the slab. Okay, so higher effective depth below the column increases the moment of inertia of the system, which increases the rigidity of the slab. Okay, however, when we remove this additional part from the below, we can reduce the weight of the slab by without compromising on the stiffness, and that's why we say that we have an increased stiffness to weight ratio. Because when we are creating these sections, we are reducing the slab area from lower stress regions and not from higher stress region. This higher stress region which is present just above the column, it remains the same. So that's why we are not compromising on the stiffness much, but we are effectively reducing the weight. Okay, that's why it is like stiffness to weight ratio has increased. Okay, not just decrease in weight. Now tell me the answer for question number 4. If the what will be the maximum diameter of rebar that I can use if I have a 125 thick slab? So I told you the limits that are mentioned in IS code. What was the limit for maximum bar diameter? Does anyone remember? Okay, so IS code says that the diameter of reinforcing bar shall not exceed 1/8 of the total thickness of the slab. Okay, so maximum bar diameter which I can use it is 125 upon 8. Okay, so that value will be around 15.6. So we can say 16 rebar is the maximum bar diameter I can use for this 125 thick slab. Okay, so this becomes a very important design criteria where later on we'll see how we will use this criteria. Okay, next question: in a flat slab without beams, the column drop or capital is mainly provided to. So what those these column drop or column capitals and drop panel do?
Improve your shear resistance. B.
B. Improve shear resistance.
Yes. So what happens when we provide these column capital and drop panel? The punching shear failure which was occurring in flat plate system, it is compromised a bit. Okay, because of the presence of secondary elements which are distributing the shear load. So that's why we say we improve the shear resistance of the system. Okay. So in the flat slab without beam, punching shear becomes critical. But when we have a drop panel, we have a thickened slab portion. So you can see here near this part, there is a thick slab portion which is present around the column, and we have a column capital also where we have a thick increased column cross sectional area. Okay, instead of this we have an increased cross sectional area of column. So this and this thickness increase and enlargement, it increases the critical shear strength of the joint, and which improves the shear capacity. Okay, question number 6: the deflection contour diagram of a two-way slab under uniform loading would resemble. So how would a deflection contour look like? How a two-way slab deflection will look like?
B. Parabolic straight
So one of you is trying to answer, but I'm not able to hear. Uh, I guess there's some problem in your mic. You can type in the chat box.
I think C, sir.
Anyone else wants to try? Okay, so it can be, we can say, circular counters or elliptical counters. Okay, both can be there. Okay, but they are centered along the mid at the mid span. Okay, so this is the pattern of counter you will see. Okay, so in two-way slab, since deflection is occurring in both the direction x and y direction, why? Because load transfer is along all the edges, so the shape is like a bowl like shape it will create. Okay, and with maximum deflection at the center and minimum deflection at the edges. Okay, so at different segments, if we'll see how the deflection will occur, it will take a iso deflection, it will be a iso deflection line. By iso deflection we mean that it is circular or elliptical but centered along the mid of the slab. Okay, so that's why you can see either it is a circular counter or a elliptical counter centered at the mid span. Okay, so this was about basic types of slab. Okay, now let's see what IS 456 code says about design of a reinforced concrete slab. Okay, so first we'll have a quick look on one-way slab design, though it is not the part of the NPTEL section that we discussed, but it is also it is still important for us to have a brief overview of design. Okay, so the analysis and design of one-way slab, it is done like a beam of 1 meter width. So we saw beam design. Okay, reinforced concrete beam design. The slab design is done in the same way. We divide a slab into different parts. Okay, as a 1 meter width beam. Okay, and we design for this, and we assume that it will run throughout the slab. Okay, so in this, what we do, we will first select an L by D ratio in the range of 25 to 30 for simply supported slab. Okay, and we'll calculate the effective depth. Okay, so first step is like using clause 23.2, we need to select the effective depth of my slab. Okay, based on assuming one L by D ratio. Then we'll calculate the effective span, L effective. Okay, which for which we saw the criteria 22.2. Okay, so we'll calculate the effective slab, and we calculate the total factored load acting on the slab, which will include self weight, floor finish, and live load, and these value we can get from IS 875. Okay, once we know the total load and L effective, we'll calculate the bending moment and shear, taking 1 meter as the length of shorter span. Okay, then we'll check whether this D that we provide is good enough or not. So we'll calculate the minimum depth required for resisting the limiting bending moment. So from limiting bending moment that we can get, if we know the steel that we are using, we can get the limiting bending moment value, mu limiting, and for this mu limiting, what depth is required, that will calculate. And if the provided depth is more than the required depth, it is okay, we can continue ahead. If the provided depth is less than the required depth, then we need to redesign the section. Okay, once our effective depth is fixed, we'll calculate the area of steel required per meter of slab, and we'll determine this diameter and the spacing of the reinforcement. So this part is similar to how we design a reinforced concrete beam, just we are taking B equal to 1 meter now. Okay, once we have determined the area of steel required, the diameter of the steel, and the spacing between the reinforcement, we'll calculate the area of distribution steel. So this was longitudinal rebar. Now we need to provide distribution reinforcement also, for which we will use the area as 0.12% of gross area if we are using deformed bars, and 0.15% of gross area if we are using plain bars. Okay, and then we'll check the deflection again. So since we have provided tensile reinforcements, tension reinforcement, now with modification factor, we'll again check the deflection, which whether it is under limit or not. If it is under limit, it is okay. If it is not under limit, then we need to again redesign the section. And finally, we'll check for shear and provide the we will do the design for stirrups the similar way with that we do for B. Okay, so this is just a basic procedure how we design a one-way slab. Now the same procedure we use in two-way slab also. So first, once we have distributed the load For each direction, when we want to estimate the longitudinal reinforcement area, the design procedure is the same. So that's why I listed the design of one-way slab first before going towards two-way slab. Now, for two-way slab, IS 456 categorizes them into two divisions. Okay, so we have simply supported two-way slab and we have restrained two-way slab. Okay, so why such division? To consider the effect of corner uplift that can happen in a two-way slab. So if we talk about simply supported two-way slab, there is no adequate provision to resist torsion at the corner and to prevent corner from lifting. Okay, so when we talk about a slab, okay, if there is no restraint provided on the side, we know this deflection is occurring in both the direction, and due to this deflection in both the direction, this corners they can lift up. Okay, so that's why there are two types of two-way slabs: simply supported and restraint supported. So in restraint, what happens, these corners they are prevented from lifting up, while in simply supported they are not prevented from lifting up. So we need to provide additional reinforcement at the corner also to prevent this upliftment. Okay, simply supported two-way slab, there is no adequate provision to resist this torsion at the corner and to prevent corner from lifting. Okay, and what IS code says, at least 50% of the tension reinforcement that we provide in the mid span should extend to the support. So whatever reinforcement we are providing in the mid span, 50% should extend to the support, and minimum, and the remaining 50% it should extend within zero point 0.1 L and point or zero point 0.1 LX or zero point 0.1 LY of the compression zone of the support. So how, what do we mean by this? We'll see in the next slide when I will show you a diagram of how reinforcement distribution is done. Now, for calculating moment along both the direction, code has given these equations. So mx is equal to alpha x times w times lx square, and my is equal to alpha y times w times ly square. And here this alpha is defined as the bending moment coefficient along x and y direction, and its value it depends upon ly by lx ratio. Okay, so here ly is the longer length and lx is the shorter length. So ratio of longer length to shorter span, this ratio determines the value of alpha x and alpha y. So knowing the value of lx by ly, using table 27 of IS 456, we can get the value of alpha x and alpha y. Okay, once we know the value of alpha x and alpha y, we have moments along both the directions, so we can do the reinforcement detailing following the same steps that we saw in one-way slab design. Okay, here in the first figure, you can see how reinforcement detailing is done. So if we have AS1 reinforcement as tensile reinforcement, this 50% of AS1 it will continue till the support. Okay, remaining 50% we need to carry in the compression part within a distance 0.1 L of the support. Okay, for edge support this is 0.1 L, and for middle support this factor becomes 0.15 L. Okay, and to bend the bars from tension to compression side, we need to start it from 0.15 times L1 at the corner and 0.3 times L1 at the 0.25 times L1 at the middle part. Okay, so this is what that clause means. 50% is extending in that same side, and the remaining 50% it continues in the compression side, in the opposite side. Okay, so this diagram just shows a basic cross sectional view of how reinforcement distribution is done. Okay, and to and for torsion, code says that we need to provide mesh reinforcements near the corner as shown in this figure. Okay, within a distance L by 1 by 5 of in both the directions. So L by 5 in both the direction. Within that distance from the corners, we need to provide mesh reinforcement. Okay, so this mesh reinforcement it needs to be provided both at the top and the bottom, and the area of this mesh reinforcement it should be one fourth of the area of steel. Okay, so whatever area of longitudinal bars we are providing, three-fourth of that area we need to provide in the tension and the and at the top at the and at the bottom as mesh reinforcement. Okay, so like suppose we are providing a 10 mm longitudinal rebar at a spacing of 200 mm center to center. So per meter it will be area times the distance. Okay, so three-fourth of that we need to provide in this section. Okay, so per meter with whatever area of longitudinal bar we are providing, three-fourth of that area of longitudinal bars we need to provide as mesh reinforcement. Okay. Now, for restraint supported two-way slab, these slabs are supported on beams or corner to prevent lifting. Okay, so in simply supported two-way slab, there was no limit on lifting. We need to provide additional torsion reinforcement, but in restraint supported two-way slab, we have prevented the lifting by supporting slabs on beams or corners. Okay, so since these slabs are restrained apart from movement near the midspan, there is negative movement that can arise on the support also because they are restrained. Okay, so we have four moments here. We have positive movement near the midspan in both x and y direction, and we have negative moments near support in both x and y direction, and these moments they are represented by these four equations. Okay, mx negative, which is alpha x negative times w lx square, mx positive alpha x w lx square, my negative alpha y negative w ly square, and my positive alpha y positive w ly square. Now the value will depend upon the this value of alpha x and alpha y. It will depend upon the restrained effect at the ends. So based on restrained effect, there can be nine classifications of slab. There is interior panel, which is free from all the sides. There is one short edge discontinuous panel. Okay, so this edge is discontinuous, other three are free. Okay, the one long edge discontinuous slab can be there, two adjacent edge discontinuous slab can be there. There can be two short edge discontinuous, two long edge discontinuous, three edge discontinuous, and one longer edge continuous, one shorter edge continuous, and four edges discontinuous. So there can be slabs, nine different classifications of slab. Okay, and in this figure you can see how these slabs will be located. An interior slab will be discontinuous from all the sides. Okay, and edge slabs, they will be either be discontinuous continuous on shorter side or on longer side. So based on different types of end restraint conditions, these values alpha x and alpha y can change. And to determine these value of alpha x and alpha y, we have a table 26 in IS 456. Okay, so suppose we take an ly by lx ratio of say 1.5, and we have two adjacent edges discontinuous. So we have this case, two adjacent edges discontinuous, so we will lie in this bracket. Okay, so for such case will have negative moment at the continuous edge. So alpha x negative will be this value, alpha x positive will be this value, and along longer direction alpha y negative will be this and alpha y positive will be this. So based on the table we can get the value of bending moment coefficients. Once we know the bending moment coefficients, we know the moment in for all 4 points. So we again, following the steps that we saw in one way slab design, we can design the two-way slab also. Okay, so let's solve one numerical to understand the application of this approach. Okay, so this is the numerical. I will mute myself for a minute. Just think how you will go along with this question, and just tell me what will be your process, how you will start with this question. I will mute myself for a minute. Let just think about the question. So can anyone tell me how they will proceed along with this question? What will be the steps of design? So in the question, you know the grade of concrete, grade of steel, you know the Ly value and Lx value, and you know the boundary condition, and you know the floor finish load. Okay. So what will be the different steps of design? Can anyone unmute and tell me? Okay, so first of all, we need to check whether it is a two-way slab or not. Okay, so we'll check Ly by Lx ratio. Then we'll check the dimension. Okay, so we will assume an L by D ratio. We'll calculate the effective depth. And based on effective depth, we'll assume a cover and a reinforcement diameter to get the total depth. Okay, once we know the depth, we'll calculate the dead load, live load, and floor finish load. From this, we'll have the total factored load. Okay, and then we'll calculate the alpha x and alpha y value, both alpha x positive negative and alpha y positive negative, because we know the Ly by Lx ratio and we know the boundary condition. So it is one short and edge continuous. So you can see in this blue diagram here, this blue slab section that we are designing, so only one short end is continuous. Okay, so once we know alpha x and alpha y value, we will get the mu value in all four direction. Then as we checked in one way slab, we'll check the whether the d that we have provided is enough or not by calculating mu limiting. Once we know whether the depth is safe or not, we'll calculate the reinforcement. Okay, in the similar way that how we do for a reinforced concrete beam. Okay, once we know the reinforcement, we'll decide the spacing and the we will define the spacing of the reinforcement. Okay, so let's see step by step. So step one is to check whether the which type of slab it is. So my Ly by Lx ratio. So Ly it is given as 4.85 and Lx is given as 3.15. So this ratio it will come out to be 1.54, which is less than 2. So we can say that it is a two-way slab. Okay, now in each first step of design is to assume a L by D ratio. So I will assume L by D ratio as 32. Suppose I am taking as 32. So my D effective depth D will be equal to Lx by 32. Okay, so it will be 3.15 divided by 32. So that will give me a value of 3.15 meter. So this I need to multiply by 1000 divided by 32, so this will give me a value of 98.4 mm. Okay, so once I know the effective depth d, I will assume a clear cover of 20 mm, and a rebar diameter, suppose I am providing it is 8 mm diameter rebar, suppose we are using for design. So we can calculate total depth as effective depth plus clear cover plus diameter of rebar by 2. Okay, so this will be 98.4 plus 20 plus 8. So it will come around 122.4 mm. So round it off, I will take total depth as 120 mm. If I take total depth as 120 mm, my effective depth will become equal to 96 mm. Okay, so this is the values that we'll use. Okay, so now we know the effective depth. Okay, now I will do the load calculation. So how we'll do the load calculation? So dead load will be nothing but the density 25 kilonewton per meter cube times the total depth and the width, which we'll assume as 1. Okay, so it will be 2.5 kilonewton per meter. This will be my dead load. Live load as per for industrial flooring, it is taken as 3. So 3 into width of the section we are assuming as 1, which will give us 3 kilonewton per meter. Floor finish load, it is given to us 0.5 kilonewton per meter. So total load is 2.5 plus 3 plus zero point 0.5, which will be equal to 6 kilonewton per meter. Okay, So factored load will be 1.5 times 6, which will be 9 kilonewton per meter. Okay, so generally for safety we can increase this load by zero point 0.5 kilonewton further, just to account for any additional kind of load that can act like some sudden loading conditions or some temporary live load which can act due to machinery. I will increase this total load by zero point 0.5 kilonewton, okay, just for safety. Okay, so if I will do that, we'll get the total factored load as 1.5 times 6.5, so it will be 9.75. So this is our assumption. Not always we need to increase the live load. We can keep whatever we are getting from floor finish, dead load and live load, so that load also we can take. Okay, I'm increasing by zero point 0.5 just to take into account an additional safety factor if needed. Okay, so we know the total factored load, so W value we know. Now we need to calculate alpha x and alpha y value. So for this, we know Lx by Ly ratio is 1.54, and we have this case, one short edge continuous. Okay, this second case is what we are dealing with. Okay, so in this case, if we go at this block, okay, we will get the alpha x and alpha y value. Okay, so we have alpha x positive as 0.057, alpha x negative it is 0.044, alpha y positive is 0.037, and alpha y negative is 0.028. Okay, so once we know alpha x and alpha y value, we can calculate the moment. So along shorter direction, mu negative, it will be alpha x negative, which is point z alpha at mid span. The moment will be point zero at not so at the corner. The moment will be 0.044 times 9.75 times L square. So shorter direction length was 3.15 square. Okay, so this will give me a moment of 5.5 4.26 kilonewton meter. Similarly, we can calculate for others also, 0.057 times 9.75 times 3.15 square. So this will give me a value of 5.51 kilonewton meter. Then along longer span, again it will be positive moment, it will be 0.037 times 9.75 times 4.85 square. So it will be 3.58 kilonewton meter. And positive negative moment, so this was positive moment at midspan, and at corner negative moment it will be 0.028 times 9.75 times 4.85 square. Okay, so this value it may come around 2.71 kilonewton meter. Okay, let me just check. I guess the values are opposite. Okay, so this value is, it is 6.42. I mistakenly entered like and this value will be 0.037 into 9.75 into 8.49. Okay, so you can have a cross check again. I'm just showing you the step how the calculation is done. Okay, once we calculate the moment, we can check for mu limiting. So for Fe 500 grade steel, mu limiting will be given by 0.333 FCK BD square. So this value will come out to be 0.333 FCK BD square. So mu limiting we can get from the code Okay, so from this you can do the check for required minimum depth. Okay, and then we will do the reinforcement detailing. Okay, so mu value we know for all four cases. Okay, positive and negative along longer and shorter span. So once we know the mu value, we know this relationship that we saw in the reinforced concrete beam. Okay, so mu value we know, fy we know, and we know b and d. Okay, so if we know all these parameter, we can estimate the area of steel reinforcement. Once we know the area of rebar, how much spacing we need to provide the area of one bar, that we know it will be from 8 diameter rebar we are using. So we can calculate the area of one bar divided by the total area that we are getting from here into 1000, because width of one section is 1000. So from that we'll get the spacing. Then the AST that we are calculating, we need to check again the AST minimum also. So whatever AST we are providing should be greater than AST minimum. If it is less than AST minimum, then we need to provide AST minimum reinforcement. And spacing that we are providing here, it should be less than minimum of 3 times diameter and 300. That also we need to check. Okay, so in our case, it is 3 times the diameter times 300, so it will be 288 so spacing should be less than 288 always. Okay, so this d parameter, let me check once. 3 times the effective depth. Okay, this is effective depth, I mistakenly said it as diameter. So effective depth we have already calculated is 96. Okay, so 3 times 96 or 300, so it will be 288 so spacing shall be less than 288 and this minimum reinforcement, it will be one, it will come out to be 144 meter square, square. Okay, so this is the minimum reinforcement that we need to provide. So whatever value we are getting AST value, we need to check against these two provisions before giving the final calculation. Okay, so for mu values, that whatever we have calculated for 3.58 kilonewton meter, when you will calculate AST, it will come out to be 88 millimeter square. But we know code says that AST minimum should be 144 So we will provide 144 millimeter square area. Okay, and spacing, when you will estimate spacing, it will come out to be 348 Okay, so this is the area. Okay, area of one bar, we know how we will calculate area of one bar. It will be 3.14 into 4 into 4. So that will be equal to 50.24 millimeter square. Okay, so this is area of one bar. Total area we know whatever we have provided. So 50.24 divided by 144 into 1000, so it will give me a value of 349. Okay, now the spacing is more than the maximum spacing limit that we have, 288 so we'll provide the minimum spacing in this case and minimum AST in this case. Similarly, you can design for other sections also, and you can determine the area of reinforcement required and the spacing of reinforcement required. Okay, so this is the procedure of design of a two-way slab based on the design table that is given in the code. Any doubt in this question? Any clause that we have used which is confusing? Any doubt? Was the question clear to everyone? Okay, so the process was, initially we checked the type of slab, then we checked the dimension. We took the initial dimension, we did the load calculation, we determined the moment. Okay, for moment we determined alpha x and alpha y value based on table, and then we calculated the area of reinforcement and spacing. So this is something that you need to take care very well. Okay, in exam if question comes, you need to take care of these two clause. Okay, because answer will have this also and the area that you are determining also. So sometimes when we don't remember these clause, our answer can be incorrect. Okay, so just remember these two clause are very important when you are finally giving the spacing and the area calculation. Okay, so these two can be tricky in exam. okay, in questions. Okay, so let's see ahead now. So now, right now we talked about beam supported two-way slabs. So these slabs that we were talking about, they were all beam supported two-way slabs. Okay, now for drop panels and column capitals, okay, as per is 456 code, what code says about their dimension? So the dimension of drop panel, code says it should be at least 1/6 the effective length of the slab in both the direction. Okay, so suppose this is my column. Okay, this is my drop panel and this is my column capital. The green one is column capital and this violet one is drop panel. So for the dimension of drop panel, code has given a provision. So it should be at least equal to 1/6 of the center to center distance along both the direction between columns. Okay. Uh, Okay, and for column capital, code says that irrespective of the slope or in drop. Okay, so this is my drop. Okay, this is the actual drop. Okay, so irrespective of the slope of this drop, code says that we need to consider this as the effective vertex area which will be loaded. Why is that so? So as per clause 32.2.3 of IS 456, they say that the portion which is lying in the vertex angle of 90-degree is structurally useful for a column capital. This remaining portion, it is not useful for column capital. So when we do the design, we just consider this internal area which is under 90-degree. Okay, so only that portion of the column capital which is within a pyramid or a cone with vertex angle of 90 degrees should be considered for design. Okay, and as per clause 35.1.3, near support, that is over column the critical section. Okay, where we determine negative moment, it should not be greater than or equal to 0.175 times the L. Okay, so these two clauses are explicitly mentioned for column capitals. Okay, and for drop panel, code says these limits which are mentioned. Okay, so these things you need to remember, or it may be asked in the question about this clause, okay, or this value. Okay, so these things you need to remember. Now, in such flat slab and flat plate system, when there is no beam to carry load, special design methods are needed. One such design method is direct design method. Okay, so we can say that the direct design method is a simplified approach for analysis and design of two-way slabs such as flat plates and flat slab that are supported directly on column without beam. Okay, so this method is provided in clause 31.4 of IS 456 and it actually originates from ACI 18318 code, the ACI code, American Concrete Institute code. Okay, now why we call this method as direct design method? Because in this method, the design moments, the M value, they are obtained directly from simple formulas and coefficient without any need or any structural analysis. So directly using some coefficient values, we can obtain the design moments. So that's why we call it as direct design method. Okay, and the entire procedure of the design is divided into four simple steps. So first we compute the total design moment from factored load on the panel. Once we know the total design moment, we distribute it as positive and negative moment according to some fixed ratio. We further divide this moment between column and middle strips. So we do longitudinal distribution of moment, we do transverse distribution of moment. Once we know the moment in each section of a slab column junction, we do the reinforcement designing. Okay, now just to clear one confusion in IS 456, we have two distinct direct looking method. Okay, for two-way slab design. Okay, we have this code coefficient method also that we saw right now earlier based on alpha WL square value, and we have this direct design method also that we are seeing here. Okay, so both of them are direct design method. Okay, this is also direct method. From alpha value and knowing the load, we can calculate the moment without doing any analysis. And this is also direct design method, where again there are some alpha values from which we can calculate the moment. But both they apply for different structural system, and they are based on different principles. Okay, so what is the difference? This table shows the difference between two methods. So this alpha L square method, alpha W L square method, which is also known as code coefficient method. So it is also known as code coefficient method. Okay, so this method is for two-way slab supported by beam, whereas this direct design method is for flat split and flat slab system where there is no beam in support. So this is applied for beam supported floor, and this is used for flat slab system in commercial building. Code cohesion method, it is based on elastic plate theory, and this direct design method is based on simplified frame analysis. Here we find moment using alpha value using table 26 that is present in code, and here we find moment using distribution ratios. So we will see ahead how we determine this distribution ratios. This code coefficient method, it is a traditional IS code method for ordinary slab, whereas this direct design method, it originated from ACI code. Okay, and why it is called direct? Because directly from coefficient we are getting moment, and this is called direct. Why? Because from load we can get the strip moments. Okay, in longitudinal and transfer direction without any analysis. Okay, so these are key differences of both code coefficient method and direct design method. Now, in direct design method, there are the code defines some limitations, or we can say some kind of assumptions for the application ability of the method. Okay, what are these limitations and key assumptions? So first, there must be three continuous span in each direction. So when we are applying code coefficient method, there should be three span in each direction. So you can see 1 2 3 span here, and 1 2 3 span here. Okay, so three continuous span in each direction should be there. Each panel must be rectangular with a longer to shorter span ratio of less than 2. So each of these panels should be a two-way slab. Okay, the column must not offset by more than 10% of the span. So if this is the centroid of the span, this offset in the column should not be more than 10%. Okay, so that is what code is saying along both axes. Okay, the successive span length in each direction must not differ by 1/3 of the longer span. Okay, so this is one more limit, and the factored live load must not exceed three times the dead load. So the live load which is acting, it should not be greater than three times the dead load. Okay, so that is one more criteria. So if any one of the following assumption is not valid, the code says that direct design method won't be safe and efficient way to predict moment and reinforcement distribution. So for such cases, we need to go for detailed structure analysis for design. Okay, we can't use the direct method. Now, for those systems where direct design method is valid, the method involves three steps of design. First is the determination of total static moment. Okay, so suppose we have divided the entire floor in east-west direction in multiple continuous span configurations. We have EW1, EW2, EW3, and EW4. So for one such frame EW3, we have the lateral dimension as L2. So total static moment for one span strip of L1, and internal length of Ln, we can for this strip. Okay, this middle strip, the total static moment we can calculate using this formula, W2 WU L2 into Ln square by 8. Okay, now what we mean by static moment and how it is distributed further. So static movement means the total movement in the slab section based on the load acting on the section. And this moment includes both the negative moment and the positive moment which is acting. So positive moment in the midspan and negative moment near the support. When we add both positive and negative moment, we get the total static moment. Okay, so we can say m naught is equal to ms plus mc, and to find ms and mc and further distribution, we have step 2 and step 3. Okay, so when we come to step 2, we do the longitudinal distribution of moment. Okay, so this total static moment, how it is distributed longitudinally, that is step 2. Okay, longitudinal distribution of moment in slab. Okay, So code says that there are two types of slab system. There is internal span and there is external span. Okay, for internal span, distribution is simple. Okay, 35% of the static moment it goes to the middle part, and 65% goes to the edge. Okay, but for external slab, the distribution of moment is not direct. It involves an additional factor q. Okay, so for middle moment, this starting moment is given as 0.63 minus 0.28 upon q times m naught, and for inner edge it is given as 0.75 minus zero point 0.1 by q m naught, and for outer edge it is zero point 0.6 m naught by q. Okay, and this q value it is given by this formula 1 plus 1 by alpha c, and alpha c is nothing but the ratio of stiffness of column to stiffness of slab. Okay, so why we are doing summation? So summation is for adding stiffness of all the columns at the exterior joint in a section, and summation ksb is this flexure stiffness of slab in the direction of movement, that is along L1 direction. Okay, so once we get the ratio of these stiffness, we can determine the alpha c value. Once we know the alpha c value, we can determine the q value. Once we know the q value and knowing the static moment value, we can determine the moment distribution along longitudinal direction. Okay, now once we have the longitudinal distribution, the last step is the transverse distribution. So in transverse direction, there are three sections. There is middle part, which is known as column strip, and there are end parts which are known as half middle strips and half middle strips. Okay, so the division of moment in transverse direction again depends upon external support and internal support. Okay, so you can see there is movement in the middle, positive movement, it will have distribution in transverse direction, and negative movement will also have distribution in transverse direction. And this distribution, it will depend upon whether we are near the interior column or whether we are talking about exterior column. Okay, so here you can see, for positive moment distribution in transverse direction, it is always the same. Okay, 60% goes to the middle part, to the column strip, and 20% goes to the edge strip. Okay, so 60% is going to middle part and 20% is going to the edge part. However, for negative moment distribution, there are changes. Okay, so this is from IS 456, what code says about moment distribution. Okay, so this chart shows the entire moment distribution in transverse direction, and it is as per clause 31.5.5 of IS 456. So at exterior support, negative moment distribution depends upon the column wall width. If column wall width is more than zero point 0.5 times L, we say that the column strip will have the all the moment, and the half middle strips which are present at the edges, they will have no moment. Okay, but if column wall width is less than 0.75 times L2, this L2 is the length in the transverse direction, then the moment distribution will be based on these two formulas. Okay, so this is for negative moment is exterior support. Now at interior support, the moment distribution is simple. The column strip has 75% movement, and half strips will have 12.5% movement in each direction. And positive movement for all span, whether it is exterior support or interior support, it remains the same. 60% is in the middle, and 25%, that is 12.5 and 12 point, so this is 20, not 12.5. 20% will be in the half middle stretch, which are at the ends. Okay, so this is how we distribute the moment along transverse direction. Okay, so once we have the longitudinal moment distribution, okay, these are longitudinal moment distribution. So once we have those moment distribution, those moments are, they are further distributed in transverse direction also. Okay, so this was all about direct design method. Now let's see some question to understand this. Okay, first of all, try to answer these three questions, and in the meantime, if you have any doubt, you can ask. Okay, what will be the answer for question number 8? Can anyone tell me? Why is direct design method not valid when factored load exceeds 3 times the factored dead load? So we saw in the assumption, when live load is greater than 3 times the dead load, direct design method is not applicable. Why? What is the reason? Can anyone tell me the answer?
Maybe C sub, it violates the assumption.
No, there is no nothing like that. The correct answer is A. Okay, so the code says that when live load is more than three times the dead load, the total moment that is acting on the slab it is very high, and for such high moment, direct design method is not efficient. Okay, so that is a simple reason that code is saying. Okay, that you can remember. Question number 9. Which of the following condition does not invalidate the use of direct design method? So just focus on this word. Does not invalidate the use. Okay. So I have given you four conditions. Okay. Now, which of these conditions will remain true and which three conditions are false for the direct design method? We are saying does not invalidate. So which is valid? It means which is valid. So what will be the answer? Can you tell me the answer? Just read all the options. You will find which one is odd one out of from this. I was not able to hear you. Can you speak again? The correct option will be D. Okay. Why? When span ratio is 2.3, it is greater than 2. Direct design method is not applicable. Factored load is four times the dead load. Again, direct design method is not applicable. There are only two continuous span. We saw in the assumption we need at least three. So again, direct design method is not applicable. And H column offset is 8%. So we had a limit of 10%. 8% is less than 10%. So for this, direct design method will be applicable. Okay, so that's why this is the correct option. Okay, so you need to remember these assumptions. Okay, one questions can be asked just based on the assumption. Okay, so you need to remember what all are the conditions for the application of direct design method. Okay. Now, question number 10. I have a flat plate system which has a panel size. So, I have given you one such panel. Okay. So, this is the panel that I am talking. For one panel size, I have given it is 6 meter cross 6 meter, and the factored load which is acting on this panel is 12 kilonewton per meter square. So, what will be the total design moment, total static design moment? Can anyone do the calculation? So we saw the formula for total static design moment. Can anyone tell me what is the formula? Okay, so formula for total static design moment is W into L2 into ln square by 8. Okay, so when we are talking about panel size, it is ln and L2 value that is given to us. Okay, so we'll get 12 into 6 into 6 into 6 divided by 8. So it will be 324 kilonewton meter. So this is my total static moment that is acting on the panel. Okay. Okay, now let's see one proper numerical where we'll see the distribution, how distribution is done. Okay, so this is the question, an exterior top panel. So just read the words. Exterior top panel of a flat slab floor system to be designed by direct design method. The center to center distance between column is 6 meter in longitudinal direction and 7.5 meter in transverse direction. Slab thickness is given as 200 mm and supports are 400 cross 400 cross square columns with a story height of 3.5 meter. We need to assume EC as 30 GP and WU as 12 kilonewton per meter square. For this, first question says compute the stiffness parameter alpha C at the exterior joint of the longitudinal direction, distribute the total static moment in longitudinal direction, and compute the distribution of moment in transverse direction. Okay, so just think how you will proceed along with this question. Okay, and then I will tell you the solution. Just read the question again, think about which section we are talking, and then I will tell you the solution. Okay, I will mute myself for a minute to let you think about the question. In the meantime, if you have any doubt regarding this question, you can ask, or any doubt regarding direct design method, you can ask. Okay, this is a very good question that if you understand this question completely, any question that will come in the exam, it will be easy for you. Okay. So can anyone tell me how we'll solve the first part? How you will calculate the stiffness parameter alpha C? Okay, so we know alpha C is given by this formula, summation of Kc upon summation of Ksb. So Kc is the stiffness of column and Ksb is the stiffness of B. Okay, so we know Kc, it will be given by 12 into E into Ic by Hc, because we will assume that the column ends are fixed condition. Okay, so for those columns we know Kc is given by this formula. Now why this? Okay, so this comes for fixed when it is fixed at both ends. Okay, and in direct design method, when we are evaluating flexure stiffness of a column, we assume that we have column in a continuous frame and both ends of the column are considered to be restrained. Okay, so if it is not explicitly mentioned in the question, we assume fixed condition of column only. Okay, and for slab, we know KSB is given by E into ISB upon L. Okay, why? Because slab is a continuous section along the span direction, and restraint to the slab is provided on the column strip. Okay, it is not concentrated. Okay, it is not fixed. Okay, so generally for slab, this formula is used for calculating the stiffness. Now, for column, since it is an exterior column, okay, we have kcs, it will be summation kc will be just 1 kc. Okay, why? Because we are talking about an exterior top panel, so there is column below, there is no column above. Okay, so that's why summation kc will be just 1 kc that we are talking about. Okay, and ic we can calculate by bh cube by 12. Okay, so bh cube by 12, so it will be zero point 0.4 into zero point 0.4 cube by 12. So 400 cross 400 column it was given to us. So it will be 2.13 into 10 to the power minus 3 meter to the power 4. So this is IC. So KC 12 E to 12 into E into IC by HC. So and you will substitute the value. KC will come out to be 2.19 into 10 to the power 8. Okay. Similarly, ISB, it is BD cube by 12. So B into d cube by 12. So d will assume as 1 meter width of slab. D it is given as 200 mm, so zero point 0.2 cube by 12. So I will come out to be 6.67 into 10 to the power minus 4 meter to the power 4. Okay, we know ISB. So KSB I can calculate as E into ISB upon L. Okay, so E I know 30 GPa, ISB we have, and L also it is given to us. It is along the longitudinal direction, it is 6 meter. So when you will substitute all the value, KSB will come out to be 3.30 into 10 to the power 6. Okay, so alpha will be ratio of Kc upon Ksb. So this ratio it will come out to be 2.19 into 10 to the power 8, 2.19 into 10 to the power 8 divided by 3.30 into 10 to the power 6. Okay, so this ratio alpha c it will come out to be 65.7. Okay, from alpha c we can get the value of q. Okay, so q will come out to be 1 plus 1 upon 65.7, so it will be 1.015. So this is the value of q. Okay, now from this we can determine the total static moment. Okay, so total static moment, after this we can determine total static moment. So wu is given to us as 12, L2 is 7.5, ln will be 6 minus zero point 0.4. Okay, so we know ln is the clear distance of the slab, so we need to subtract the dimension of the column, so that's why 6 minus zero point 0.4 square by 8. Okay, so this value it will come out to be 305.8 kilonewton meter per meter width of the slab. Okay, so we know the total static moment. Now we need to do the distribution of this moment. Okay, so for longitudinal direction, negative exterior moment, we know it is given as 0.65 times m by q. Okay, so it will be 0.65 into 305.8 divided by 1.05, 1.015. So it will come out to be 195.83 kilonewton meter per meter. Negative interior moment, it is given as 0.75 minus zero point 0.1 by q times m naught. Okay, so it will be 0.75 minus zero point 0.1 by 1.015 times 305.8. So it will come out to be 199.22 kilonewton meter per meter. And positive midspan moment, it is 0.35 times m naught. Okay, so this will come out to be 0.35 into 308.5, 305.8, so that will be equal to 107.03 kilonewton meter per meter. Okay, so so since this is an exterior slab, I have done the calculation for exterior moments only. Okay, so the middle moment will be this value. Okay, 0.63 minus 0.28 by q times m now. Okay, I wrote wrong formula. 0.63 minus 0.28 by q times m naught. Okay, so that value it will come out to be 107.3. Okay, so this is the moment distribution for exterior slab. Okay, now in transverse direction, we need moment distribution. So I will assume this middle strip is equal to 0.25 times L naught. Okay, so that assumption it is mentioned in IS code somewhere, that we need to assume the width. Okay, so width of middle strip, it either it will be given in the question or we need to make the assumption. So I am assuming it is 25% times the length in the transverse direction. Okay, so once we know this in transverse direction, so 0.25 times L naught it will be equal to 0.25 times 7.5, so that will be equal to 1.875 meter. Okay, so this will be my middle strip, and from 7.5 minus 1.875 will be distributed as edge strips. Okay, so first of all, in transverse direction, we need to check first this criteria. Okay, a column wall width should be is either is it greater than 0.75 times L naught or not. Okay, so for this, we have column width is given to as a 400 mm, and 0.75 times L2, it will come out to be 0.75 times 7.5 meters, so that will be 5625 mm. Okay, so since my column width is less than 0.75 times L2, I will use these formulas, these second formulas for distribution of moment in negative direction. Okay, so we'll have column strip. Okay, negative moment and exterior support. Column strip will be given by the width of the strip, which is 1.875 times upon L2, which is 7.5, into moment at the exterior column, which we calculated, it was 195.83. Okay, here we calculated 195.83, so this will give me a value of 48.96 kilonewton per meter, kilonewton meter per meter. And for half middle strip, it will be zero point 0.5 times 1 minus 1.875 upon 7.5 times 195.83. So it will be 73.44 kilonewton meter per meter. Similarly, for interior, we know the distribution is simple. 75% of interior negative moment, 199.22, will go in the column strip. So that will be 149.42 kilonewton meter per meter. And for both the half strip, it will be 12.5% of 199.22. So it will be 24.90 kilonewton meter per meter, which will go in the half strip. And middle moment, it is zero point 0.6 times the middle moment in the longitudinal direction. So it's 107.06, 64.22 kilonewton meter per meter. And half middle strip, it will be 20%. So 107.73, 21.41 kilonewton meter per meter. So once we know movement for all the sections, now we can design the reinforcement. Okay, like we saw in the two-way slab design, similar design method can be offered for reinforcement detailing now. Okay, so this is how we do the application of direct design method. So in exam, either one of the parts can be asked to you. Okay, either this calculation of AC or distribution of moments can be asked to you. Okay, so how it is done, that I have shown in this question. Okay, any doubt in the question how application is done for direct design method? I hope this was clear to everyone.
Yes, sir.
Now another method for design of two-way slab is equivalent frame method. Okay, so as you can see in the figure, it shows the top view of a building floor, but we can see in this floor there are different shapes of column. Okay, there are circular columns also, there are rectangular columns also, and there are different slab segments also within the same section. Okay, so if we take this segment, okay, okay, and we see the side view. Okay, so there is corner edge slab, there is slab with column capital, there is slab with drop panel and column capital, and there is beam supported slab. So in the same segment there are different types of slab system present. Now for such complex system, code coefficient method and direct design method can't be used. Okay, so for such system we have equivalent frame method that we use. Okay, so in equivalent frame method, the slab is divided into series of two-dimensional frames in each direction, and positive and negative moment is calculated using elastic frame analysis. Okay, so process is the same. We divide slab in different segments and we calculate the moment. Okay, this method is very satisfactory for symmetrical as well as for unsymmetrical or unusual loading frames. And once we have found the moment, it is distributed to slabs as we do it in the direct design method. So once we calculate the moment, the distribution is the same as we do in the direct design method. Okay, now if we see what different components are present in a equivalent frame, so in the figure we can see we have a slab beam member, which is present in longitudinal direction, okay, along the span length of L1, okay. uh, then there is a transverse beam which is present along the span length of L2, okay. So if we are calculating the moment along this length, this moment will act as a torsional moment for this transverse beam, okay. So and there is there is column also which is present, okay. So there are three critical members that are present in the equivalent frame, okay. Now to create the equivalent frame out of this, what we do, so for column and transverse beam, if we see in 2D, okay, so if we see a frame structure, this is my floor in longitudinal direction L1. The transverse direction is, it is hidden, it is like this behind, and these are columns below and above, okay. So what we do, we have for columns above and below, we simplify this into a simple frame diagram. So this above and below column, we will combine it as a single column, okay. So this is the combination of above and below column, and we have transverse beam also which is running horizontally. So this transverse beam and this uh, combined column, they are combined together to produce an equivalent column, okay, like this, okay. So in this equivalent column, we have both columns above and below, and we have transverse beam which is there, okay. And the stiffness, it is given as KEC, stiffness of equivalent column, okay. So this is how we take columns and torsional member into account for equivalent stiffness. And for slab beam members, we saw that slabs can have different types there can be different types of slab as shown in the figure. There is edge slab, beam supported slab, there is column capital supported slab, drop panel plus column capital supported slab, and beam slab, okay. So if we have very simple prismatic beam, we know for unit rotation theta, moment required is 4 EI by L, and 50% of this moment is it is carried out at the far end, okay. And free end moment, it is given by this formula, okay. However, in our case where there are complex slab systems, this value of K carryover factor and fixed end moment, it would be greater than all these values. So all my values will be greater than these because members are stiffer at beam column side, column slab joints, and slabs with drop panel column capital also have a stiffness greater than the simple prismatic beams, okay. So what equivalent frame method does, it helps us to calculate this variation in stiffness into account by using Hardy cross method, okay. So Hardy cross method is commonly used in ACI code, and it gives us the list of all possible combinations of slab beam junctions which are possible, and for those combination, what will be the value of K carryover factor and free end moment, all we can get from this method, okay. So it is not as simple as a prismatic beam, okay. For complex system also, we can calculate the stiffness parameter using this Hardy cross method. Now, before seeing the table from Hardy-Cross method, we need to understand why stiffness of a member in slab beam section is changing. So, very direct answer is due to change in the effective depth. Now, in in stiffness, we have EI value. Stiffness is represented by EI. E doesn't change much, but I changes due to member thickness change. Okay, so if you see a slab system with drop panel and column capital, at section A, the modulus of elasticity, the moment of inertia, it will be I1. However, at section BB, this moment of inertia, as the depth of the section is increasing, the moment of inertia will also increase. Okay, so it will be I2, and this I2 will be greater than I1. And when column capital will also come into account, this moment of inertia will further increase from I2. Okay, so that's why we say the member stiffness is not as simple as prismatic beam. It changes when we have more stiff systems that are present in a column beam junction, or a column slab junction, okay. And the same thing can be seen for column also, irrespective of the type of slab, whether it is a flat slab or a without beam, or with drop panel, or with beam, or with the column capital, any type of slab. In the middle part, the flexural stiffness, it is given by EC times IC. However, as we go at the edge, okay, the beam and the slab also come into picture, so the moment of inertia increases significantly due to very high value of this length, okay. So, and I we say tends to infinity. Okay, so in this also I changes as the member thickness changes. So that's why we can't just use the simple formulas of 12 ei by l or 4 ei by l anymore. We need to take assumption of changing effective depth and changing section type also into account. Okay, now how we calculate equivalent stiffness of column? So we know equivalent column has two parts. Okay, it consists of columns above and below the slab, and it consists of torsional edge beam which is present on both side of the column. Okay, so if a column is subjected to a unit rotation theta, the same rotation will be reflected in the beam in the transverse direction. So if at the beam column junction the deflection is theta, then at far end the deflection will be greater than theta. Okay, so we say theta A and theta C will be greater than theta B. Why? Because at junction there is greater depth. Okay, so theta will be smaller. However, at this point the depths are lower, so theta will be more. Okay, so as a result, we can say that average rotation of the H slab is greater than whatever rotation is there at the beam column junction. And for this, we calculate the equivalent column stiffness. So to find the equivalent stiffness, column above and below. Okay, so we have this frame structure. So this column above and below, they are in parallel, so their stiffness will directly add as summation kc, and these two columns, they are in series with the beam. So for that we need to use this parallel law of equivalency. Okay, so 1 upon kc is equal to 1 upon summation kc plus 1 upon kt. So from this we get the value of kce. Okay, and this, if we know the value equivalent column stiffness and we know the moment, so we can calculate the average rotation of the edge beam also. So okay, so this is theta ce. Okay, if we know the column rotation, we can calculate the beam twist that can also occur. Okay, so this is the importance of kce. Now for calculating the stiffness of torsional beam, code has given this formula: summation of 9 ECC upon L2 times 1 minus C2 upon L2. Okay, so EC is the modulus of elasticity of concrete, C2 is the width of equivalent rectangular section, and T is the torsional property of section, which is given by this formula that is given in the code. Okay, so here you can see it is summation of some formula. X is the shorter dimension and y is the larger dimension. So code says that this division, suppose we have a joint like this. Okay, so we need to divide this joint into rectangular sections, and this section division shall be done in such a way that if x1 and x2 are there, and if x1 is greater than x2, then y1 should be also be maximum. Okay, so if this y1 is possible, we need to provide this y1 if x1 is greater than x2. Okay, so among these two choices, if x1 is greater than x2, I need to do division like this and not like this. Okay, this is what is mentioned in the code. Okay, so that is how we need to calculate this torsional constant c. If we know the value of c, we can get the stiffness of the torsional beam. Column stiffness will get directly from the formulas 12 ei by l hc. So we can calculate summation column stiffness, and adding everything we will get the equivalent stiffness of the column. Okay, now, to find equivalent parameters, Hardy-Cross method has given standard charts and table which are there in ACI code. So here one such example is for flat plate system. So you can see there is B slab directly supported on column. Okay. So for such system, we have this table that is given in the question uh, in the code. Okay, so here we have some notations n and f. So n represents the near end and f represents the far end. So suppose we have distributed uniformly distributed load, so near end distance and far end distance, it is given with respect to this load. Okay, so if we want to calculate stiffness of this column, then near end will be this and far end will be this. If I want to calculate stiffness of this junction, near end will be this and far end will be this. Okay, so based on the value of this width of column at near end and width of column at far end and the transverse length L1 and L2, uh, this ratio of these values and the uniform loading condition, we can calculate the value of K uh, carryover factor and FEM value. Okay, so for this, there is this chart given in the code. So for example, if I have CN1 and CN2 equal to zero point 0.1, okay, and I have uniformly distributed load all across, okay, so from here to A here, if I have uniformly distributed load, so for such cases, my carryover factor K value will be 4.18, carryover factor will be 0.51, and uniformly distributed load throughout, it will give me a FEM value of M value of 0.0847. Okay, so once we know these value, we can calculate the free end, fixed end, free end moment, and we can calculate the effective stiffness of the section, so equivalent stiffness of the section. Okay, so this was for flat plate. Similarly, for flat slab with drop panel also, code has given the table. So they assume the dimension of drop panel as L2 by 3 and L1 by 3, and for these dimension, again for near end and far end, based on the load distribution, a table has been given in the code for calculating the carryover factor, stiffness value, and the FEM value. And for columns also, there is design table given in the question, in the code. Okay, so if we have a, this is for flat plate, and this is for flat slab system with drop panel, and this is for flat slab system with drop panel and column capital. So H is the center to center distance between the floor, and HC is the clear height of column. Okay, so HC value will change based on the presence of flat plate or fat slab, but H value won't change. So one ratio is H by HC, and TA by TB ratio, here TB will remain the same, the mid thickness of floor slab. TA value will depend upon whether it is a flat plate or a flat slab. So for flat plate, TA is this. For flat slab, it will be this plus the thickness of drop panel, and for flat slab with column capital, it will be the total thickness, TA plus thickness of this drop panel plus thickness of column capital. So this TA by TB ratio will also change. So based on this ratio and this ratio, we can calculate the value of equivalent stiffness and carryover factor in column also. Okay, so these three tables are given in the ACI code, which will aid the design of a equivalent frame method. Okay, now based on the understanding of equivalent frame method, just try to answer these three simple questions, and in the meantime, if you have any doubt regarding this segment, you can ask. Okay, what will be the answer for question number 12? In equivalent frame method, the purpose of introducing torsional member along column line is to. So why we are having torsional member in equivalent in such frames? So when we calculate equivalent column stiffness, why we are considering torsional member also in that? Can anyone tell me the answer? Yes. So we saw, I guess, in the discussion when we talk about torsion members, when we talk about torsional beam, there is rotation that is happening in the beam. Okay, and we introduced the torsional member in design just to take into account the compatibility of due to twisting that is produced at the junction. Okay, so for that we are introducing torsional member in equivalent stiffness calculation. Question number 13. The stiffness of a slab beam member near the column joint is high. Why it is high? Why near joint stiffness of a member is high?
B.
I was not able to hear.
B.
Yes. So when we talk about section near the joints, we know there are drop panels and column capital which are also present, and due to this the equivalent thickness of the section increases. So as the thickness of the section increases, the moment of inertia increases, so that's why then equivalent EI value increases near the joint. Okay, I guess someone was trying to ask something. Was there any doubt? Okay. Question number 14. The coefficient C in the torsional stiffness. This coefficient C, it depends upon which factor. Can anyone tell me the answer? What is this coefficient C dependent upon? Yes, it depends upon the shape of the torsional section. So we saw this formula, if you remember. Okay, so shape dictates the value of C. So code says that if x1 is greater than x2, when then we need to provide y1 also, which is maximum possible. Okay, so the distribution in which how we'll distribute the section, it will determine the value of C. Okay, it doesn't depend upon any strength value or D value or span value. It just depend upon these the shape of the section, distribution of the shape. Okay. Now let's see one simple numerical, how we calculate the equivalent stiffness of column. Okay, so here in this question we have given an H column in a slab with transverse beam with support dimensions given in the question. So this is my column and this is my transverse beam. Okay, and it is an H column. Okay, so its effective height is 3.2 meter, and moment of inertia is given this, and modulus of elasticity is given to you. In transverse direction, length is given as 6.5 meter, and width of the equivalent rectangular column, this is C2 value, it is given to us as 0.75 meter. Assuming both ends of the column are fixed, we need to compute the net column stiffness, torsional stiffness, and equivalent column stiffness. Okay. So can anyone tell me what will be the net column stiffness? So just look at the dimensions and read the question once and just tell me what will be the net column stiffness. You know the E value, you know the moment of inertia, modulus of elasticity, you know the height of the column, you know the length of the column in transverse direction, everything you know. So how you will calculate the net column stiffness? What will be the formula? So it is an H top column. Okay, at the top corner. Okay. Okay, net column stiffness. Since the far end is given to us as fixed, okay, we have fixed. Code has question has given to us that assume both end of the columns are fixed. So column stiffness K will be given by 12 EI by HC. Okay, so it will be 12 into E 25 GPa to 10 to the power 9 into I 0.045 divided by HC, which is given as 3.2. Okay, so upon calculation, you will get K value will be equal to 4.12 into 10 to the power 9. Okay. Now, since this is a top H column, there is no column above. So Kc will be just this value. Okay. So there is no column above. So we won't multiply this by 2. It will be just this value. If would have been a middle H column, then there is column above and below, both are there. So we'll multiply Kc by 2. But since in the question it is given, it is top H column. Okay. So we don't need to multiply it by 2. Okay. So column stiffness will be just due to one column. Now, second part, torsional stiffness. So for torsional stiffness, we know this is the formula summation E 9 ECC upon L2 into 1 minus C2 by L2 to the power cube. So L2 it is given to us, it is equal to 7.6.5. C2 it is given to us, it is equal to 0.75. Okay, but C value we need to calculate, and C value we know it is given by this formula. Okay, so in this we need to do the division properly. Okay, so if I assume this is 1 and this is 2, okay, so x1 it is 100 mm and x2 is equal to 200 mm. Okay, so what we have learned in the division rule, if the x which is greater, it needs to be provided larger y. So I will divide it like this. Okay, so this is my first column. Okay, this will be my one section and this smaller one will be my second section. Okay, so like this we'll do the division because this is greater than this, so y I need to provide greater to this x2. Okay, so y1 will be equal to 600 minus 200, which is equal to 400 mm, and y2 will be equal to 500 mm. Okay, so when you will do the calculation, you will substitute the value of x and y here. So it will be c will be equal to 1 minus 0.63 times 100 by 200 into 100 cube into 200 by 3 plus again 1 minus 0.63 times 200 by, this is 100 by 400. Okay, 200 by 500 into 200 cube into 500 by 3. Okay, so in exams you may get question like this section is given to you and this formula is known to you. Okay, so you need to calculate the value of c, so you need to remember how you need to do the division. Okay, so upon from this you will get c value will be equal to 1.11 into 10 to the power minus 3 meter to the power 4. Okay, once we know the C value, we can calculate the KT value easily. So KT will be nothing but 9 into 25 into 10 to the power 9 times 1.11 into 10 to the power minus 3 whole upon L2, it is given as 6.5 times 1 minus 0.75 upon 6.5 cube. Okay, so KT it will come out to be 55.51 into 10 to the power 6. Okay, so we know KT value, we know KC value, so we can calculate equivalent stiffness of column using this formula. So when you will substitute the value, it will come out to be 5.43 into 10 to the power 7. Okay, so this will be my equivalent stiffness. Okay, so this is how we use the codal provisions for calculation. Okay, we need to take care the stiffness of column. Okay, which type of fixed end condition or continuous end condition, what is given in the question, where the column is located, whether we need to multiply by 2 or not. Then for stiffness of torsional beam, you need to be careful in calculating the C value. Okay, once you calculate the C value, KT will come out, and then you need to calculate the equivalent column stiffness like this. Okay, any doubt in this question? How we did the calculation and how we proceeded along with the question? Any doubts? Okay, so this was all from today's session. We talked about RC slab and its categorization based on location and dimension. We talked about IS 456 design for one-way slab and two-way slab. We are talking about moment factor distribution using code coefficient method. And we discussed design of flat slab and slabs using flat plates using the direct design method. And we talked about equivalent frame method and how equivalent design parameters are computed using Hardy-Cross method. So this was all for today's session, and with this we'll end the course. Thank you.